Logo, Indeed. One search. All jobs. Text. At Indeed Eng. Monthly Tech Talks at Indeed's Austin headquarters. Engineering.indeed.com. A presentation slide. Title: Logrepo. Enabling Data-Driven Decisions. Jeff Chin speaking.
As Jack said, tonight we'll be talking about Logrepo and how it enables data-driven decisions here at Indeed. My name is Jeff Chin, and I'm a software engineer. Indeed is the #1 job search site worldwide.
New slide, with a bar graph, map, and text. Title, Scale. Bar graph title, Unique visitor in millions, average monthly number over the 3 months ended. It increases steadily, from nearly 0 to over 100 million. Then, a world map with the majority of the countries highlighted. Text. More job searches worldwide than any other employment website. Over 3 billion searches per month. Over 24 million jobs.
It's available in over 50 countries and 28 languages. And every month we have over 100 million unique visitors. I help people get jobs by working on the Indeed Apply team. And our goal is to make it easy for job seekers to apply to jobs.
New slide. An Indeed job search page showing a list of results for the search, Software Engineer, Java, in Austin, Texas.
The way this works is that people first perform a search on Indeed. We return a list of job results that match your query.
New slide, focusing on one search result. Text. Front-end software engineer, new product. Apply with your Indeed resume. Sponsored by Indeed.
And a lot of these jobs will let you know that you can apply with your Indeed resume. This lets you know that it's integrated with Indeed Apply. Once you click on one of these jobs, you're taken to the job description page where you can see the full job description. And you'll notice that on the right-hand side, there's a bright orange button that says Apply Now.
Text. Apply now. Please review all application instructions before applying.
Once you click on this Apply Now button, if you're one of the tens of millions of people who already have an Indeed resume, the only thing you need to do is fill out an optional cover letter and then click Apply. If you do not already have an Indeed resume, then we'll ask you for some contact information such as your name and phone number, and then we'll ask you to choose a resume to upload from your computer or mobile device.
New slide. Title. Job seeker flow using Indeed Apply.
So what just happened was, job seeker performs a search, they view a job, they click Apply Now, and then they submit their application. We need to know that all of these things happened, because knowing how users are interacting with our systems will help us build better products.
New slide, with a simple 2-bar graph. Title. Likelihood of applying to a job. The shorter bar, less likely, says, have to upload a resume. The taller bar, more likely, says, have Indeed resume.
Once we have this information, we can analyze it and see interesting insights. For example, if you already have an Indeed resume when you click the Apply Now button, you're over 50% more likely to complete the apply process than if you had to upload a resume. We have lots of questions across all of our products. Things like, what percentage of applications are using Indeed resume? How many job seekers are searching for Java in Austin? How often are job seekers editing their resume once they've uploaded it? And how long does it take for us to visit employer sites and aggregate their jobs? These questions get a lot more complicated too. For example, how many applications to jobs from Career Builder by job seekers who search for Java in Austin use an Indeed resume? Is the percentage of people who do this different on web than it is from mobile? And has this changed over time? With more information, we can make better decisions. So we need to log all the events that happened: job searches, clicks, and applies. And for each event, we also need to log everything. We never know what effect a change might have.
New slide. Title. Better decisions. Text. Use empirical data to make decisions.
The types of things that we log are things like client information, user behavior, system performance, and the A/B test groups that a user is in for a request. Once we have this data, we can use it to make better decisions. We don't want to be making decisions based on assumptions, nor the highest paid person's opinion. So our objective is we want to collect data on user actions and system performance from all of our applications in all of our data centers across the world. At Indeed, we have a few principles that we apply to all the systems that we build. They need to be simple, fast, resilient, and scalable. By simple, I mean that the system should have an easy interface to use. It should be easy to both write logs as well as read them. We also want to reuse familiar technologies. We don't want to reinvent the wheel where we don't have to. This means that we like to reuse technologies that ops already understands very well, things like gzip and rsync. The system should also be fast. Writing logs from our application should have no negative impact on runtime performance. In addition, once logs have been written, we want the data to be available very soon for consumers. The system should also be resilient, and in it, write should be durable.
New slide. Text. Does not lose data in spite of system or network failures.
Once an application writes a log, it should show up in the system, even in spite of network failures or system downtime. Last, the system needs to be able to scale to handle the large amounts of data that we throw through it. And as of today, this is on the order of terabytes each day. The system needs to be powerful enough to represent any kind of data that we need it to. And we should store all of data for all of time, unsampled. Events should be stored at least once so that writes are never lost. We may store it multiple times for redundancy purposes, but consumers should never read a duplicate event. It should be very easy for developers to add new data to logs as we roll out new features. And on the flip side, it should also be extremely easy to access our logs in large amounts at a time for a given time period. And this is our most common access pattern.
Slide text. Time range-based access.
We look at everything that happened over a certain time period and then analyze it.
New slide. Title. Non-goals.
Because of this is our most common access pattern, we didn't optimize for random access to individual events. We also care more about completeness of logs, so we didn't optimize for real-time access. In addition, we did not have explicit support for complex data types, but I'll elaborate more on that later. Our solution is called Logrepo. It's a distributed event logging system, and we've been using it in production for all of our applications since the end of 2006. Inside Logrepo, every event is called a log entry. And inside of a log entry, everything is stored as a string. Data is URL encoded into key value pairs, exactly like the query string in a URL.
New slide. Title. Organic click log entry. It's a string of symbols, letters, numbers, and other data, long enough to form a paragraph block.
Here's what an example log entry looks like for an organic click event. It's a large blob of text. But once you insert new lines after ampersands and URL decode the values, it becomes much more readable.
New slide. He's inserted line breaks and removed a majority of the percentage symbols. Then he highlights two of the lines. Text. Type equals org, click ampersand. Job ID equals 500 ampersand.
And you can see that we can support both text data as well as numeric values. This log entry format has a lot of advantages. First of all, it's human readable. This means that anyone, not just developers, can take a log entry and get useful information out of it. Log entries also have arbitrary keys. There's no set schema ahead of time, so developers have it very easy in order to add new data to logs. And because of the format, it's very easy to append the data as we get new data.
Slide text. Low overhead to add new key value pairs.
Log entries are also self-describing. So just by looking at keys and their values, you can determine what you're looking at, whether it's timing information or a user search query. And it's easy to parse in any language. Each log entry has two required keys, UID and type. Type is simply an arbitrary string which describes the contents of the log entry.
He has an example URL. This type string is type equals org, click. Then, a new slide. Title, UID format. For this URL, UID equals a string of seemingly random numbers and letters.
UID is always the first key in a log entry. It's a unique 16-character base 32 string, which means it uses the characters 0 through 9 and A through V. And a UID encodes several pieces of important information. First of all, it encodes a timestamp of the event.
New slide. Title, UID breakdown. The first part of this UID is 18 DUCM8, U. Text. Date equals 2014-01-10. Time equals 9 hours 35 minutes and 24 seconds. 357.
This has millisecond level granularity, and we have enough bits for it to represent 1,000 years of time. Next, it also stores some server information on the server ID and application instance ID that produced the event.
This part of the UID is 50 NK2. Text. Server ID equals 1512. App instance ID equals 2.
Last, it has some version information as well as a random value.
This part of the UID is 3QH. Text. UID version equals 0. Random value equals 3921. New slide. Title, UID generation.
Since UIDs are unique, this random value is essential for making sure we don't have any UID collisions within a given millisecond. And this random value is just a number between 0 and 8,191. This means that we can support up to 8,000 events per an application instance per millisecond. And this UID format also has some benefits. It stores all the useful information I just described, plus it compacts it into a nice format which is useful when you're processing millions or billions of logs.
Slide text. Compact format reduces memory requirements. Easy to compare or sort events by time.
Because timestamp makes up the most significant bits in the UID format, you can take whole log entries and easily sort them by time. So let's take another look at what I talked about earlier. A job seeker comes to Indeed and they search for jobs. They click on some of the results and maybe apply to a few of those jobs. All of these events are part of the same flow, and it's important that we're able to tie these events together in order to fully understand the job seeker's experience. To do this, we model the events into a parent-child relationship. And in this model, children can reference their parent events by what we call a tracking key, or TK for short.
New slide, with an example URL. It starts with &TK equals, and follows with the UID we broke down a minute ago.
This TK contains the value of the UID of the parent event. And it's important to note that this abbreviation of TK is just a convention. It can be called anything. So children know who their parents are, but parents do not necessarily know who their children are, because most of the time, once we log the parent event, we don't yet know if there are going to be any child events. This is an extremely powerful model for us.
New slide, with 2 example URLs. Text. An organic click points to the search it occurred on. The first URL has a UID, then, type equals job search. The second URL has a different UID, then, type equals org, click. Followed by, TK equals the first UID.
So for example, if you perform a job search and you click on one of the events, the log entries may look something like this. You have your parent job search entry, and then you have your child organic click entry, and that has a TK pointing to the UID of the job search event. And we have lots of child events for job search alone. This includes things like sponsored job clicks, JavaScript errors, job alert signups, and many more. So how does Indeed Apply use Logrepo? Here's a slightly modified version of the events I was talking about earlier.
New slide, a simple flowchart. Title, Job Seeker views a job. There are 4 related events in the flow. Text, from top to bottom. Job view, load Indeed Apply, user submission, post to employer.
First, a job seeker views the job page. And when this happens, we create a log entry called the view job log entry. As part of this page load, we execute some JavaScript that enables the Indeed Apply functionality on the right.
The text, Load Indeed Apply, has an arrow pointing over to the previously mentioned Apply Now button.
This creates another log entry that refers to the tracking key, or UID, of the view job entry. Once the user has filled out the information and submitted the application, we log another event, and this refers back to the JavaScript loading event. Finally, once we have the application on the back end, we will post it to the employer's applicant tracking system, and this logs yet another event that refers to the submission event. All these events form together to form a chain together and give us an idea of a job seeker's path through the application process, and then what we actually did with their application once we got it. Another use case that we have for parent-child relationships is for something we call the JavaScript latency ping.
Slide text. At start of page load, browser executes JS to ping Indeed.
And what happens is when you perform a search, your browser will execute some JavaScript that makes an HTTP request to Indeed. Once we receive this ping, we log an event.
New slide. Title: Parent Job Search and Child JS Latency Ping. Two example URLs. The first one is a UID followed by type equals job search. The second is a new UID followed by type equals lat. And then TK equals the first UID.
So these events might look something like this. You have your parent job search entry, and then once we receive the latency ping, we create a latency event. A really convenient feature of how we log the parent event's UID in the child event is that it makes it very easy for us to determine how much time has elapsed between two events.
New slide. Title: Subtracting UID timestamps yields duration. Text: UID timestamp. January 9, 2014. 0 hours 0 minutes and 5 seconds. 253. TK timestamp. January 9, 2014. 0 hours 0 minutes and 5 seconds. 046. Latency equals 207 milliseconds. Approximates perceived latency to job seeker.
And to do this, we parse the timestamp information out of both the child event and the parent UID. And then we take the difference of these values. So here we can see that there was a latency of about 200 milliseconds. And what this does is approximate the time from when we received a request to when a job seeker begins rendering their response. And we're able to see this information. Here's a graph of the perceived latency from our West Coast data center to Washington and California.
New slide, a line graph. It measures JavaScript latency delay in milliseconds. The California line runs along near the bottom, with less delay, while the Washington line is higher up, running across the center and top of the graph.
And in this graph, California is in red, and it's about 175 milliseconds as the median value. Whereas in Washington, it's about 190 to 200 milliseconds for their perceived latency. This makes sense since our West Coast data center is located in California. Writing log entries from your applications is extremely easy. This is all the code you need, and I'll go through it step by step. First, you use a factory method to create the log entry. And all you need to do is pass it the log entry type.
Slide text. Factory dot, create log entry. Open parentheses, quote, search. Close quote, close parentheses.
The factory method is in charge of creating the UID, and it'll use the current time as its timestamp. Once you've created the log entry, you populate it by calling the setProperty method, and that takes a key and a value.
Slide text. Entry.setProperty. Open parentheses, quote. There are separate entries for query, account ID, and elapsed milliseconds. New slide. Title, lists.
Earlier, I talked about how we did not have explicit support for complex data types, yet we needed Logrepo to be powerful enough to express anything that we need to. So lists is a more complicated type, and the way we represent lists is by taking elements and delimiting them by commas. Once you've written this to a log entry, the commas get URL encoded into %2cs.
In the slide example, there's the string group, foo, comma, bar, comma, baz. In URL form, it becomes foo, %2c, bar, %2c, baz.
But this compresses back down very nicely. Taking that a step further, we also support lists of tuples. And we encapsulate tuples using parentheses. Within a tuple, elements are delimited by commas just like they were in lists. For example, when you perform a job search, we log all of the job results we return to you. And for each job result, we like to log both the job ID and the relevancy score, along other things. So here's what that looks like.
Slide text. 2 jobs with job ID score. String jobs equals, quote, open parentheses, 123, comma, 1.0, close parentheses. Open parentheses, 400, comma, 0.8, close parentheses. Close quote.
It's important to note that if we need to, we can also URL encode the value within the list, which means that it'll be doubly encoded in Logrepo.
New slide. Title, committing a log entry. Text, entry.commit, parentheses.
Once you've fully populated your log entry, you simply call commit on it. And at this point, it hands off the log entries to a system that's maintained by our operations team. And Jason Copy will explain more on that.
Thanks. I'm Jason Copy, and I'm one of the systems administrators here at Indeed. And I engineer systems that help people get jobs. Prior to the log repository, we still needed to understand what was happening inside of our applications. The way that we did this is using debugging logs. Developers and systems administrators would manually look at these logs and figure out what the applications were doing.
New slide. Title, before Logrepo. A box labeled, App Server. Inside it, the text, Application Log4j, points to the text, Debugging Logs for Humans.
And we use a logging framework called Log4j to do that. Log4j is an open source Java logging framework that enables our developers to write code that specifies what should be logged and enables the operations staff to create a configuration that defines what goes where. In Log4j's terminology, the where is called an appender. And these could be things like files or SMTP servers. So prior to log repository, we were using Log4j and a file appender to create these debugging logs for humans to read. And we wanted to reuse this powerful paradigm when creating the log repository. And so that's what we started with. Log4j using a file appender to create log repository logs, which were meant to be consumed by programs. However, we also realized that we wanted redundancy for the log entries as fast as possible. And what this meant is writing to multiple locations.
New slide. Title, Redundancy from the start. Text, write to local disk.
The first destination we wrote to is a file, and we used the file appender to do this. We also wanted to write to 2 separate remote servers, and we needed to find an appender that helped us do this. When we began to investigate how to write to remote servers, it was clear that the overwhelmingly popular platform for doing this is a protocol called syslog, which is a protocol for transporting messages across an IP network established in the 1980s.
New slide. Title, Using Log4j with syslog.
Out of the box, Log4j only supports UDP-based syslog appenders. And UDP is a network protocol that could result in data loss. For the log repository, we wanted to avoid data loss at all cost. So we wanted to use a network protocol called TCP, which guarantees data transfer.
New slide. Title, Creating a Reliable Appender. Text, created by Indeed.
So we created something called the syslog TCP appender, which is a TCP-enabled Log4j syslog appender that buffers messages in memory before transporting them to the remote server. This makes the syslog TCP appender resilient in the face of short downtimes for the network or the remote server. We also needed to choose a syslog daemon. We chose something called syslog next generation, which is simply a syslog daemon that supports TCP, and it was created in 1998. Putting all of this together, we were able to achieve redundancy with Log4j by using a file appender to write to the local disk and using 2 instances of the syslog TCP appender to write to 2 separate remote servers.
New slide, a diagram. Title, Redundancy over TCP. 3 separate boxes labeled, syslog server number 1, app server, syslog server number 2. The syslog TCP appender connects app server to the others. App server inner text, application log4j, file appender, local log repo files.
And this is what the system architecture looks like, with the application using Log4j and these 2 types of appenders to ultimately write to 3 separate destinations. On each of the syslog servers, the syslog-ng daemon receives unsorted log entries from the cluster of applications and immediately flushes those entries to files on disk and to files that we call raw logs. So now the architecture looks like this, where the application is using Log4j to write out through the syslog TCP appender to the syslog-ng processes, which write into these raw logs. Up until this point, we've optimized the system for redundancy. And at this cost, the raw logs on the syslog servers are probably out of order. And this happens because all of the applications that are writing to the syslog server are independent. They're not coordinating together to ensure that the entries arrive at the syslog server in sorted order. And this is OK, because the next major component in the architecture is called the log repository builder, or builder for short. And its responsibility is optimizing the log entries for our read access patterns. And it does this by sorting, deduplicating, and compressing the log entries. So now our architecture looks like this, with syslog writing the raw logs.
New slide, a diagram. Title, Builder Architecture. A box labeled syslog server number 1. Inner text. Syslog ng, write, raw logs. Builder, read, raw logs.
And when we introduce the builder, it reads from these raw logs. In order to sort, deduplicate, and compress the log entries, ultimately writing out into files, into a log repository archive, files that we call segment files. Each of these segment files that the builder creates has one log entry per line. And the files are also sorted in UID order. And because the timestamp and date are the most significant bits, it means that these files are each sorted in time order. And because there are a lot of repeated strings in these files, we see a really good compression ratio. On average, these segment files compress by 85%. We also choose a very specific directory structure in this log repository archive that is optimized for the way that we'll be reading the log repository later. It starts with a top-level directory for the log entry type. In this example, org-click.
Slide text. 4-character UID prefix, base 32.
The next directory are the first 4 characters of the UID for all of the log entries in that subdirectory. And because the first part of the UID is based on the timestamp, this corresponds to roughly 9.3 hours of time. So all of the log entries in this subdirectory are within this 9.3-hour time range.
Slide text. 5-character UID prefix, base 32.
Taking it 1 character further, the first character in the file name is the 5th character of the UID. Putting that together with the second directory, we have the first 5 characters of the UID. And this corresponds to about 17 minutes. And so at most, each segment file can contain log entries that span a 17-minute time window. Lastly, we have a unique number towards the end of the file name. And this is so that we can support more than 1 segment file per type per 5-character UID prefix. And the reason that we wanted to do that is so that we could better predict the resources required by this builder machine. And what that means is fixing the amount of memory that each builder process is able to use.
New slide. Title, Multiple segment files. Text. Keep builder memory usage fixed. When builder memory fills, it flushes to disk.
And since the builder uses an in-memory buffer to sort and deduplicate these log entries, when the buffer fills, it needs to flush to disk. And when it flushes to disk, it creates a new file for that 5-character UID prefix. At this point, this is what the system architecture looks like, with the 2 independent syslog ng servers receiving their own stream of log entries that get written into the raw logs. And on one server, we have a builder process that is creating this Logrepo archive. It's a small step adding rsync mirroring every minute to add redundancy for this log repository archive. And now that we have 2 separate streams of raw logs and we have the same Logrepo archive on both servers, we're able to ensure the consistency of the archive by running a delayed builder on the second server, which compares the output from the first builder to its own output and adds new segment files for log entries that were missed by the first builder. This also causes multiple segment files per 5-character UID prefix. And the next major component in the architecture is a process called the log repository reader, or reader for short. And its responsibility is to provide access to the log repository. And using a simple request protocol, the log repository reader reads the segment files from the archive and provides a sorted stream of entries to a TCP-based client as quickly as possible. The request protocol looks like this. It's a start time and end time and the Logrepo type. That's it. I want to walk you guys through an example of using simple Linux utilities to send a request to the log repository reader and receive a stream of results.
New slide. Title: Reader request using Netcat.
So in this example, I'm building the request using the protocol I just talked about. So the first field is the start time.
Slide text: $, echo, followed by a string of 13 numbers.
And the format is in milliseconds since January 1st, 1970, which is the start of Unix time. The next field is the end time, and the last field is the log repository type.
The end time is also a string of 13 numbers. The log repository type here is org, click. Slide text: send echo across a TCP session.
Sending this over a pipe to a utility called netcat, I'm able to make a connection to the log repository reader process and send it this request. And ultimately, I receive back a UID-sorted stream of log entries as a result.
New slide. Title: Reading entries from archive. 1. Isolate to the type directory. An arrow points to org, click.
Under the hood, the reader takes advantage of that directory structure that I explained in order to isolate to only the information in the log repository that the request cares about. So I'm going to walk through the same request, but detailing how the reader reads from the segment files on disk. The first thing it does is isolates to the type directory. The next thing it does is it converts the request timestamps into their UID prefixes. In this example, the start timestamp's UID prefix is 15MT0, and the end timestamp's UID prefix is 15MT7. The next thing it does is finds all of the segment files that match that first UID prefix.
Slide text. 4. Read sorted segments simultaneously, merge into a single sorted stream.
And then it needs to read all of those segment files. Now, remember that each segment file itself is sorted in UID order. However, when we're looking at multiple segment files, it's possible that all of them taken together are not sorted right now. In this example, if we were to simply stream back the first file to the client and then the second file, the client would not receive the log entries in UID sorted order.
On the slide, the first file is 1 but the second file is 3.
So it's the reader's responsibility to sort these and provide that single stream of sorted events back to the client. The reader should also make sure to never send back log entries that are outside of the request timestamps.
Slide text. 5. Only return log entries between timestamps. On the list of files, the first one gets crossed out.
Once we finish processing that first UID prefix, we move on to the other UID prefixes until we get to the last UID prefix for the end timestamp.
Slide text. 6. Read segments for each UID prefix, one prefix at a time. 7. Stop reading files when entry crosses request boundary.
As we're operating on the segment files in that last UID prefix, as soon as the reader sees a log entry whose timestamp is beyond the end timestamp, it considers that file to be done and finishes processing the rest of the files. Prior to introducing the reader, this is what our architecture looked like, with the syslog-ng servers creating the raw logs, the builder creating the archive, and the mirror between the servers. And since the reader only needs to read from the archive, this is the way that we started the architecture, with the reader simply running on the syslog servers and accessing the archive directly. And this is the architecture that worked for us for the first few years.
New slide. Title: The First Years. 2007 and 2008.
We had a single data center and a cluster of application servers, and we had these two Logrepo servers that each ran the syslog-ng the builder, and the reader process. However, as Indeed grew, we saw more job seekers using our site, and we created more products, and we expanded into more data centers, and all of this meant more log entries.
New slide. Title: Multi-data center rationale.
The reason that we moved into multiple data centers is so that we could decrease the latency for our job seekers, but also increase the redundancy of our data centers, so that if any one data center failed, the job seeker could still have a low latency experience using our site. And all of this led to happier job seekers. So when considering how to augment the Logrepo for supporting multiple data centers, we realized that the consumers of the log repository only really needed to live in one data center, which meant that we only needed to run the reader in one data center.
New slide. Title: Logrepo in multiple data centers.
However, we knew that we would have applications in every data center that would be creating log entries that we cared about. And in order to minimize the internet traffic, we decided to run the 2 syslog servers and the builders on those syslog servers in every data center.
New slide. A diagram. 3 data centers. DC number 1, with consumers, contains 2 reader servers. DCs number 2 and 3, with syslog, each contain raw logs, a builder, and an archive. These data centers mirror into the reader server 1 archive, which mirrors into reader server 2.
And so this diagram, I'm showing 3 separate data centers, and this is roughly how it works today, where on the top right, in the data center in the blue, I'll call data center 2, and it actually has the 2 syslog-ng servers with the 2 builders. In this diagram, I'm just showing the primary syslog-ng server for that data center. And on the top right, the data center in orange, data center 3, the same thing, where it's running the 2 syslog servers with the builders. And each data center independently maintains its own log repository using its own log repository builders. And then we replicate those log repositories back into data center 1, which is at the bottom, which is where our consumers are running. And the reader process reads from this archive that has all of the data center's data.
New slide. Title: Single data center archival.
When we had just one data center, this is the directory structure that we used inside of the log repository archive, with the top level being the type and the subsequent directories and files being the timestamps, the beginning of the UID.
Slide text. Event type. Org. Click means organic search result click. 25-bit timestamp prefix, base 32. About a 17-minute time period.
When we started expanding into multiple data centers, we needed a way to separate one data center from another. So we introduced a new top-level directory with the data center name.
Data center now precedes event type. Text. DC1.
And this is necessary in order to avoid collisions. In this example, I'm showing 2 separate segment files that come from 2 separate data centers, data center 1 and data center 3.
Text. DC1. DC3.
However, they share the same segment file name. And this is totally possible because the builders that created these segment files are operating in independent data centers, and they don't know anything about the other data center's log repository.
New slide. Title: UID breakdown.
We also said at the beginning that UIDs needed to be unique. So the way that we guarantee this when we have multiple data centers is by harnessing the server ID field in the UID.
He's using the original UID we broke down. The server ID is 1512. New slide. Title: Using server ID for uniqueness.
In the UID. What we do is we give each data center 256 server IDs to start. So the first server in the first data center gets server ID 0. The second server in that first data center gets server ID 1, and so on and so forth.
Slide text. 1. DC number 1 uses 0 through 255. 2. DC number 2 uses 256 through 511. 3. DC number 3 uses 512 through 767. New slide, titled The Next Years, 2009 to 2011.
And this architecture worked for us for the next few years, where we had multiple data centers, and in each of those data centers we had the 2 Logrepo servers that were running syslog-ng and the builder processes. And we had the 1 consumer data center that was running the reader and where all of the consumers lived. As we continued to grow, we had more log entries and ultimately more consumers of the log repository. And what we started to see over time is that there were a diverse type of requests that were happening. And for example, the first consumer might be looking at job search request logs from the last month. And the second consumer might be looking at resume creations over the last 2 days, and so on and so forth.
New slide, a diagram. Reader server number 1, with the reader and archive. 4 arrows point to the server. They are 1 and 2, then after an ellipses, it jumps to 100.
And to a point, this was fine. The diversity of the requests were able to get to the reader and get their responses fast enough. However, when we continued to increase the number of consumers and had an ever-growing amount of diversity, we noticed a bottleneck.
There are 2 new arrows. One is an ellipses, then the next arrow jumps to 750.
The single server that had an array of disks underneath the reader process couldn't keep up with the amount of diversity coming from all of our log repository consumers.
New slide. Title, Scaling Log Repo Reads.
And so we wanted to eliminate this bottleneck by spreading the log repository accesses across a cluster of servers.
New slide. Title, Read Log Repo from HDFS.
We were already using this thing called HDFS at the time, and it stands for Hadoop Distributed File System, which is a distributed file system that stores data on commodity machines, providing very high aggregate bandwidth across the cluster. We needed a way to bridge the gap between our existing log repository archive and HDFS.
New slide. Title, Using HDFS for Log Repo Access. 2 separate boxes, Reader Server number 1, and HDFS. The server contains an archive and HDFS contains data nodes.
So we created a process called the HDFS pusher, which, as fast as possible, takes each of the segment files from the archive and copies them into HDFS.
Now 6 arrows point to HDFS. Text. 1, 2, ellipses, 100, ellipses, 750.
Once the log repository is in HDFS, the consumers are now able to read directly from HDFS rather than accessing through that original reader server. To maintain resiliency for log repository inside of HDFS, we store each log entry on 3 separate servers and 3 separate disks. Additionally, to make the log repository available as soon as possible in HDFS, we simply mirror every segment file from the log repository archive into HDFS. What this means, since we're storing still by data center, by type, UID prefix, that we would be creating over 500,000 files per day in HDFS. And unfortunately, HDFS doesn't do so well if you try to do this. HDFS works a lot better if you have fewer files. And so we wanted a way to reduce the number of log repository files that we were adding to HDFS. And we created something called the HDFS archiver, whose responsibility it is to look at yesterday's log repository data that is already in HDFS in the segment file format and collapse those into a file, 1 file per type and 4-character UID prefix. What this means is that we'll only be adding 2,500 files per day to HDFS. And as you can see, over a month, this really starts to add up, and we decrease the number of files in HDFS and allowing us to scale our use of HDFS a lot more. Using a number of technologies that Indeed created and a number of open source technologies, we're able to create the system that we call Logrepo, the distributed event logging system.
Slide text. Created by Indeed Eng. Application: syslog TCP appender, builder, reader, HDFS pusher, reader and archiver. Open source. Log4j, syslog ng, gzip, rsync and Hadoop.
Today, the log repository for all time is approximately 150 terabytes of compressed. It has tripled in size since last January and tripled in size from the previous January. This graph is showing the size of the log repository over the last 4 years, with 2010 being on the far left, and it's barely even registering on the scale. So we're growing.
The graph measures log repo size in terabytes from January 2010 to January 2014. As it moves toward STHE right, it grows exponentially. New slide. Title: Job Search Event Set.
As an example of what we're able to do with log repository, these are the 129 different metrics that we're able to compile from the job search event set. And job search is just one of 114 different event sets that we create from the data that we log in log repository. Every day at Indeed, we create 5 billion new log entries. Our application spends 0.03 milliseconds to create each of these log entries. We add 500 gigabytes to our archive, which gets triplicated into HDFS, adding another 1.5 terabytes into HDFS. And our consumers can read this information from HDFS at an alarming 18.5 gigabytes per second. So we have hundreds of consumers that are requesting 1,000 different log repository types from the log repository every day. And to talk more about how those consumers access the log repo, Jeff's going to come back up. Thanks.
Thanks. So as Jason said, I'm going to be talking more about how we actually consume Logrepo here at Indeed. There are 4 primary types of consumers, and this includes command line access, standard Java programs, programs that use Hadoop, and monitors. As Jason described earlier, we can use command line tools such as netcat to access Logrepo. And the great thing about this is it allows us to reuse standard Unix tools and patterns in order for us to do one-time analyses of Logrepo data. So here's an example of how I would look at the slowest search times over a given period of time. First, I use netcat in order to get the stream of log entries back. Then I grep for the key and value that I'm looking for. I pass that through another grep just to pull out the value. And then I sort it in descending order. In the dark ages, before we had lots of other types of consumers, this was our most common way of looking at our log data. However, even today, it's still extremely useful. And you can do things like parse out just the query string to get an idea of what types of searches people are looking for. Programmatic access is trivial, and we can access Logrepo from Java, Python, PHP, and Pig. A typical Logrepo consumer is written in Java and runs on a single machine. These consumers tend to read one primary log event type, and they read maybe a dozen children. We call the combination of a parent event and all of its children an event set, and in total, they may be on the order of 10 kilobytes in size. One of these consumers will read millions of log entries spanning 1 day or more usually. And we run thousands of instances of these consumers every day. So this means that we're going through tens of terabytes of data in processing. Because of the amount of volume that we're going through, it's very important for us to be able to efficiently parse data out of our log entry.
New slide. Title: Efficient parsing. Text: Important for single machine consumers.
And we found that at the start, log entry parsing was just too slow. So in order to be more efficient, the 2 things we cared about were being fast and minimizing memory usage. So I'm proud to announce that as of today, we have open sourced our URL parsing library that we use internally at Indeed. And this is in charge of parsing data out of our log entries as well as query strings out of URLs.
New slide. Title: URL string parsing, now available on GitHub. github.com/indeedeng. go.indeed.com/URL parsing.
And this library can do it 4 times faster than using string.split to break out data into key value pairs and then splitting that further into a map. It also generates 50% less garbage than doing that. It's able to parse 1 million events of log entries that are half a kilobyte in size in 3 seconds. And here, I've included a link to our GitHub page where you can find all of our open source projects, as well as a direct link to the URL parsing library. And I'll bring this up at the end of the talk as well. We still ran into the limitations that a single machine can provide. So we began to use Hadoop. And Hadoop provides a reliable, scalable way of doing distributed computing. Today, most of the new consumers we write are actually using Hadoop. And as Jason said earlier, these consumers are able to read log entries directly from HDFS.
Slide text. Divide and conquer to scale.
By utilizing our cluster of machines, we're able to scale further. We also use Logrepo for monitoring. And we want to be able to monitor our business and operational metrics. After deploying new code especially, we need to make sure that searches haven't been broken, nor are they suddenly taking twice as long to perform searches. And in these cases, available soon just isn't good enough. We use Datadog, which is a third-party monitoring service. And the way it works is that we stream metrics to their third-party servers. And from there, they aggregate the information and show us dashboards in real time. The dashboards look something like this.
New slide, a Datadog dashboard. There are 2 busy line graphs. One measures job search average time US, and the other, job search average time Indeed. Both track it across an hour span.
Here's an example of average search times from instances in a data center. However, we still have the problem of needing to parse metrics out of our raw log entries. And in order to do this for Datadog, we use a language called Mini-EPL. Mini-EPL is an implementation of the Esper processing language, which is written in-house at Indeed in Python. The way it works is like SQL for streams of log entries. And even though real-time access wasn't one of our original goals, because of the nature of Logrepo and its loosely coupled components, we were able to easily extend it to get around the latency of having to go through the builder process.
New slide, a diagram. Title: Getting logs into Datadog. A server contains an application, local log entries, a Datadog agent, and Mini-EPL.
To do this, every server that has an application that produces log entries also runs a process called the Datadog agent. This Datadog agent reads those locally written log entries and passes it through the Mini-EPL, where it can then parse out the metrics we care about for monitoring. It then uploads those to Datadog HQ so that we can see the dashboards. It's important to note, however, that these dashboards they can only show us aggregate information, and we don't have fine granularity access to our data. Logrepo also provides a form of data redundancy for us, and we use that in a couple different ways. First is for replaying events. So Indeed has a feature called job alerts, and job seekers can provide a query for jobs that they're interested in, and every day or every week we'll send them an email of new jobs that match their query. After one of our deploys, we accidentally broke job alert sign up for logged in users. However, we were able to use the Apache access logs to first get the alert parameters that they were trying to create alerts for, which includes the query that they're looking for, the location that they're searching in, and the radius that they're willing to look for around their location. And these Apache access logs also included the tracking key of the job search UID of the search that they were trying to sign up for a job alert from. We were able to find these job search log entries, and from there we could figure out what account IDs were actually trying to create these job alerts. And together, we were able to recreate the job alerts for those users. Another very important thing that we use Logrepo for is for click charging. And at a very high level, this is how it works. When a user clicks on a sponsored job, first we write all the click data to a database. We then log that same data to Logrepo. Once a process is verified that the database contents match what we wrote to Logrepo, we're able to charge for the clicks, and then we can profit. So what else does Logrepo enable? It enables us to answer our business and operational questions, and from that we can make data-driven decisions. A lot of the graphs that I showed you earlier were from an internal tool called Ramses. And Ramses provides a high-performant way of querying our Logrepo data. So here's some other examples of what we can see in Ramses. For example, what is the average cover letter length for applications inside the US versus outside?
New slide, a line graph. The red line for inside the US runs across the bottom, indicating shorter cover letter length on average. The outside of US line trends closer to the middle and top of the graph.
And here in red, you can see that inside the US, cover letters tend to be about 115 characters long. But outside the US, they're more like 200 characters long. We can also take a look at things like hour by hour. How does mobile traffic differ from Japan than from the United Kingdom?
New slide, a line graph. Across the length of a day, Japan has generally higher mobile traffic than the UK. There's a big dip in the middle before it tapers back up, and the UK traffic has a similar dip at the far end of the graph. New slide, a graph. Title, Resume Creation by Country? It is a color-coded stacked area graph. Lines extend to the right, measuring the amount across time, but the area underneath is shaded in to help differentiate many different countries. The largest area is red, although it has a drop early on the left.
We can also see from what countries are users creating resumes from. At the start, we just launched resume upload for United States, which is here in red, and other English-speaking countries like Canada and Great Britain. But as we added more and more countries, we can see that the percentage of resumes created from US users decreased, and other countries began to fill up more of that space.
New slide, a line graph. Title, Email Alert Opens by Email Domain? It measures from October 2013 to January 2014. Open rates are very low for Hotmail and AOL domains. Gmail and Yahoo run across the middle of the graph before moving up into the top right.
We're also able to see from what domains are users opening our job alerts from. And the interesting thing here is that earlier in 2013, represented by the green line, which might be a little hard to see, but Yahoo actually was the domain most people are opening job alerts from. And a little bit below that are Gmail users. However, at the end of 2013, Gmail began automatically proxying image loading. And before that, users had to explicitly specify that they wanted to load images for their emails. And since the way we track people who open our job alerts is through these image pings that we get, Gmail suddenly jumped up past Yahoo as the provider that had the most job alert opens.
New slide, a simple stacked area graph. Title, Percent of app downloads from iOS, Android, Windows? It measures from 2011 to 2013. The graph is pretty evenly split between red and blue, with just slightly more blue towards the right, and a little bit of green peeking in at the top.
We're also able to take a look at from what operating systems are users downloading our mobile job search app from. Here in red is iOS, and in blue is Android. And at the very, very, very top, tiny amounts, that's Windows phones.
New slide, a spiky stacked area graph. Title, How quickly does a data center take on traffic after a failover? It measures across time. The areas from top to bottom are green, blue, and red. Red is the largest area and blue the smallest, with some somewhat severe fluctuations towards the right.
We can also see operational things like when one data center fails, how long does it take for traffic to shift over to our failover data centers? We'll talk more about Ramses in our March Tech Talk, but I just wanted to give you guys a taste of what it can do. The important thing to note is that Ramses and many other tools all use Logrepo as the foundation of their data. I'd like to now open the floor for questions on Logrepo.
People in the audience, seated, clapping. Logo, Indeed. One search. All jobs.